Okay, history. How far back does it go? It goes further back than we can possibly know because there's no records. There are some things lying around the Earth that we know that were used. For example, there's Stonehenge, the summer solstice. We've got things that go back to at least 3000 BC. You can tell were used for some kind of celestial observation. This is Stonehenge again. There's lots of alignments that have been found in Stonehenge. Over on the right is what Stonehenge, your left, is what it looked like. And here's some of the alignments that have been discovered. Constructed over a long period of time, so how far back the astronomical usage of that structure goes, we're not sure. Their models were based on something that they thought was obvious. For example, the reason the Earth doesn't move through space is if I drop something, it goes straight down. You know, if you throw something out of a car window, it doesn't go straight, it bends. So this was the kind of principles that they used to deduce their obvious first principles. So if you start off with something that's wrong, it just carries on being wrong. But interestingly, this theory, which you'll see, carried on for a long time. So here's Aristotle, a great thinker of his day, a little bit before the birth of Christ. And he perceived everything as being on perfect spheres, with the Earth being the center. This is the geocentric model. And you see his model here. He wasn't the first. There was another thinker before him, Eudoxus, and he came up with a model of 27 nested spheres that accounted for all the movements in the heavens. Aristotle, with his weight of authority, sanctified that model, and he expanded it to get up to 55 spheres that described everything they saw in the sky. And here's a simple representation of what they were thinking with the Earth at the center. But unfortunately, it did make things difficult to explain. Some of the planets are retrograde. That is, if you're looking at them with the stars in the background, they seem to move in one direction and then they'll move back again. And that is due to the relative change in position to the Earth's orbit. So here's a diagram. Here's Mars rotating round. Here's Earth rotating round. And this is what Mars looks like in the sky. It doubles back and then it goes on. The last law is for every action there's an equal and opposite reaction. This is why rockets work. The exhaust that comes out is a force and it pushes the other way. And rockets work. If you want a very simple demonstration of this law, just take your hands, put them together and push one hand on the other. Now, if you don't exert force with the hand you're pushing on, you're going to move. But if you exert force with both hands, you'll stay constant. Another example of his third law. Gravity. This is the equation for gravity. Basically says that the gravitational force between two objects is equal to some constant, which is the universal constant of gravity. We go into this in much more detail when I talk about gravity. It's then the two masses multiplied together. So in this case, me and the Earth, although I'm pretty insignificant. I'm getting more significant thanks to the buffet. And then the separation between their centers. Now we get up to the 1700s. There is a lady in this picture assisting a man here. I'm not going to say anything more right now. Who is she? Anybody know? Who is this lady? Okay, let me try and give you a clue. What's the planet?
Uranus.
I heard Uranus. Yes. Now, is that a clue? Now, who discovered Uranus? Anybody know? No?
Herschel.
No? Herschel, yes, very good, very good. My God, top of the class. I'm going to give you a complimentary dinner at a complimentary restaurant of your choice after this. Right, so this is Herschel. Who's she?
His wife.
Wife, I heard wife.
Daughter.
Daughter. Lover. Sister, very good. Another complimentary dinner. Yes, that's his sister. Very interesting, and you'll see that she was quite remarkable in her own right as we go along here. It's mind-boggling when you think about this and give it some thought. Most of the matter in the universe is not radiating at any wavelength that we can observe. At least 90% of the matter in the universe is dark, and that is a rather daunting idea. We became astronomers thinking we were studying the universe, and now we learn that we're just studying the 5 or 10% that is luminous. That's amazing, isn't it? And you look up in the sky and you see all the stars, and then most of what's out there you can't actually see. What is dark matter? Really very briefly, it is a substance that doesn't interact with electromagnetic radiation. Electromagnetic radiation is what's coming out of my laser pointer. It's light. Electromagnetic radiation is gamma rays, X-rays, microwaves, radio waves. I may have missed a couple. That's what electromagnetic radiation is. This stuff doesn't interact with it at all. It doesn't reflect it, doesn't absorb it, so it's dark. We have time for one or two questions. Yes?
Since I'm the Greek one here, I recognize names.
Yes, I bet I mangled them horribly.
No.
Oh, thank you. I said the names right.
Non-Greek question.
Yes, a non-Greek question.
Being such an intellectual scientist, do you think there is life somewhere else? We hear all this kind of...
The question is, do I think there is life somewhere else? You missed the lecture on life on other planets, didn't you? Yes, you did. I think there has to be. There's so many stars out there, and originally, yes, we didn't think there were many planets, but we're discovering more and more exoplanets all the time. I think the number I put up on the screen was 3,500 exoplanets have been discovered up to a few days back. And we're looking in such a tiny part of the galaxy. There are as many galaxies in the universe as there are stars in our own galaxy. So for us to be unique is, I think, a bit far-fetched. Excellent question. The question there was, and thank you for that one, I'll paraphrase if I may. Throughout time, we've had scientific theories that as time has progressed, we have learned have been incorrect. The question now is, under the theories we got now, would they be correct? Is that about right? Yes. Well, of course, we don't know if they're incorrect, do we? Newton's law of gravitation, for example, although it works, when you, and again this is in the gravity talk, when you look at the next step on the theoretical advancement of gravity, we get to Einstein and we get to space-time. Newton's law is an approximation, it works, but the current thinking is that gravity is really governed by curves in space-time. So that's a theory on top of a theory. That's an extension, but I have another talk that's not being given on this ship, which is outmoded scientific theories, where I actually do go into some scientific theories that were wrong and how long they lasted for. It's fascinating how long that you can be wrong. I mean, look at the geocentric model I was talking about here. That lasted for 1,500 years, and they were still able to make precise measurements with it until we got better instruments and so on. Anybody else? Thank you very much, everyone.